Okay, let me make sure this is recording my voice. Okay, it's working, it's working. Hi, you guys. I hope everyone's doing well. This is Sabrina, and I'm going to be working through the practice exam multiple choice that was provided by Dr. Bean in class for the chapters 20 up to 22. And so as I got started on this actually, and I was feeling kind of bored doing it on my own. And so I said something in the group me just in case if anybody wants to zoom in and listen to it and ask questions live. Um, Maybe somebody will, maybe someone won't. It's kind of early in the morning, but I had to do it this way so that it gives enough time in order for the video, because it's going to be really long, in order for it to upload. So let's make sure. Okay, yes, it's recording. So let's just go ahead and get started. I'm gonna write a couple things. Okay, so it says to select the best name for the compound below. So of course we're going to be starting off with nomenclature here, and hopefully when it's multiple choice, the nomenclature that can help you out and then make it a little bit more straightforward because you can do process of elimination here, but let's just try to name it as normal and not worry too much about the fact that it's multiple choice. So here we want to identify what is our highest priority functional group in this molecule. And I'm hoping that someone out there is going to say amide. So the amide is our highest priority functional group. And just looking at the answer choices, I can see that we can knock out two of these. So let's just put amide. All right. And then we want to number our parent and know which side of this functional group is our parent. And always, 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 for these carboxylic acid derivatives, you're going to want to start numbering that parent chain. The number one carbon is always going to be where? It's going to be the carbonyl. So you're going to go 1, 2, 3, right? And you want to know what your prefix is for 3, and that of course is going to be prop. So we're going to put that right in front of the amide part, and we're going to put propanamide. Let me move it a little bit closer, because we definitely don't want to have a space there for the parent. You don't want any space at all actually with these amides over here, okay? And so just from that, just by knowing our parent, you guys, we are able to zero in on what our answer choice is. But let's continue. So then we have to deal with our substituents, and our parent on the left over here, it doesn't have any. But where we do have substituents, it's going to be coming off of here, as well as here, coming off of the nitrogen. So you do want to most definitely indicate for the amides that if you have a substituent and it's coming off of the nitrogen in the amide bond, you want to indicate that, because it's different than if it were to be coming off from over here. So what we're going to do is we'll just name them as normal. So at the top we have this 2 carbon group. So how are we going to name that one? That's going to be an ethyl. And of course, where is that coming off? So this is where it's a little bit different. We have that coming off of the nitrogen, and we have to indicate that. So instead of putting a number, we're going to put a nitrogen. But we treat that nitrogen just as though it wasn't a number, okay? And then if we're looking at the other substituent coming off of the nitrogen, what we see is a complex substituent. So you have a pseudoparent and you have a substituent coming off of that. And what is that substituent going to be called? That box, the group that I circled, that's going to be called a cyano group. So it's a nitrile, and you call it nitrile when it's the parent. But when it's a substituent, we want to call it a cyano. So we have 1, 2, 3, right? And so what would be our pseudo parent when we have a 3-carbon chain? It's going to be propyl. And then coming off of that propyl at our number 1 carbon, we have a cyano, right? One cyanopropyl. All right. And that entire thing is a complex substituent. Remember, is coming off of the nitrogen. So we want to indicate that for sure. So we put in dash and put the 1 cyanopropyl. Then we're going to want to write this entire thing out in our name, right? And so we have to figure out in what order we're going to do that. So don't worry about the N in the front. You might have um, a molecule that has groups coming from here and they have numbers. So don't worry about that N in the front. What you want to worry about when you're writing this entire thing out is going to be the alphabetical order of those substituents and how they come in the alphabet. So we have E, we have C, and of course what's going to come first in the alphabet is going to be our C. So we'll put, oops, wrong one. We're going to put the cyanopropyl first. We write the entire thing out. And remember, we treat the nitrogen as though it is a number. So we want to separate it by using those dashes there. And then we continue with the ethyl propanamide. All right. So for the first one, what I would go with for my answer, it's going to be, I'd go with B. Alrighty. So let's continue on. So it's also nomenclature here. And wow, there's a good amount of nomenclature. 3 questions. So it wants us to pick the name for this one as well. So you want to identify always, 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 what is our highest priority functional group in the molecule? And I hope you guys are thinking the ester right here. So you have the ester, and we want to figure out how to name this molecule when our parent is our ester. So what we're going to want to do is we're going to want to number that parent 6. Alrighty. So whenever we have an ester, right away, since we identified that there's an ester, we could knock out one of these answer choices. So I want to leave you to that, or to figure that. Well, actually, we could knock out the 2 of these, right? So I want to leave you guys to that to try to figure out which 2 you can knock out at this step. So that's convenient. And then we want to say, how would we normally name our esters? So here we have 6 carbons in our parent. And so we're going to want to use the prefix hex. Alrighty. And in our parent, right, we don't have any double bonds, so we can continue it with hexane, right, instead of hexene. And then we have to account for the fact that we have an ester. And so for the ester, what you're going to want to do is you pretend as though, let's say you had a 6-carbon carboxylic parent basin, right, parent chain. So you would name that hexanoic, right? So you would name it hexanoic. But here we don't. We have this carboxylic acid derivative. And with the carboxylic acid derivative, what we're going to want to do for the esters, we're going to drop the oic. And what we're going to add instead is OH towards the end. So hexanoate. All right. And that would be indicative that we have this ester. Okay. And then coming off of our parent, contrary to the last problem, what we have here is carbonyl. And at carbonyl, we have a ketone. So that is a substituent off of our parent. So how are we going to name a ketone when it is a substituent? You should be saying oxo. And where is that oxo group coming off? Number 3. All right. So we have no substituents left from our parent, but we do have one coming off from the other side. of our O. So with these esters, you always want to name the parent on the very far right side. So I'd put the 3-oxohexanoate, and then you consider that R group that's coming from the other side of the oxygen, this one right here. So for example, the one on the left always is going to be, that's going to be our parent. Now the R group coming from the other side that's passed directly to the oxygen, that's going to be our R group, and we're going to name that as a substituent always, okay? And we're always going to put a space in between that group, whatever we get for it, and for example, our 3-oxohexanoate, okay? So let's see what we have going on here. So I numbered it already. You always start with number 1. Doesn't matter if you have an alkene, a double bond at the end of that, okay? Doesn't matter. So then you're going to want to say this is 5 carbons, and so 5 carbons is going to be pent, right? And we have a double bond here. So we're going to want to indicate that. And then this is a substituent, so we're going to want to indicate that with the enol, pentenyl, right? We want to say where is that alkene within our substituent? Where is that coming off? And that's going to be our number 4. All right. 4-pentenyl. Someone on the group chat said I would, but I'm too sleepy for that. Yeah, I don't blame you. So might as well put the link anyway, though, just in case later, because I probably wouldn't see it. Let's see if I can copy it. Okay. Invite, copy URL, then we can go here. Okay. So where were we? So we were saying 4-pentenyl, and so that we're gonna want to put that. I shouldn't put a parenthesis here, right? Because it's just coming off of the R group, the oxygen. So that's implied. So I feel like it disconnected. Let me pause the share and resume share. See if that does anything. So I'm not sure why it's not erasing. Because I erased something. Stop share. Share screen. Let's see if this is gonna work. Okay. I think we're back. Okay. So we have 4-pentenyl. And that is our substituent. That is our R group. So we're going to want to put in the entire name, we're going to write it 4-pentenyl, and then we'll put a space. You always want to put a space in between that parent ester as well as the R group. So that's why you have to have the space right there. And then we continue with 4-pentanol, 3-oxohexanoate. So that's what I would put for this answer. Okay, so you definitely could have knocked out the anhydride as well as the hexanone. Those are the wrong parent right off the bat. Okay, so moving on to number 3, what we have here, it's another nomenclature, and so we're going to want to pick our highest priority group as always. So what's our highest priority group here in this molecule? It should be the cyano group. So I'm going to highlight this right here. That's going to be a part of our parent, and we're going to start that carbon off. That's going to be our number 1 carbon. So we're going to go 1, 2, 3, 4, 5, 6. Okay, and with the nitriles, what you want to do when they're your parent is you just want to write it out as though it's an ordinary alkane chain. So this would be 6 carbons. So we would name this as hexane. You include the E for this one, and you just add the word nitrile at the end. You just throw in the word nitrile like that, and we go with hexane nitrile. And as you can see, I mean, that already knocks out 3 of our options, and we get straight to our answer. So you wouldn't even have to go through the process of figuring out R or S here. But really quickly, you would want to put the 2-hydroxy because our alcohol group is located at the 2nd carbon, and then we have this chiral center. So we would want to indicate the R or S for the stereocenter, and you'd pick in terms of what's your highest priority group, and we have an oxygen first, so that carbon like that. So when you're comparing between the oxygen and the carbon, that's higher priority. So we're going to want to go like that. And of course, when we make a circle clockwise, going from 1 to 2 to 3, that is going to be our R stereo center. All right. So now that's what I would put for 3. And we'll continue into some of our standard fact questions. And so it wants us to rank the compounds in order of increasing acidity. And the concept of acidity basicity is very, very important. Oh, I think it's saying that someone wants to join, but I'm not sure. So anyway, what's going on here is what we want to do when we're thinking about acidity is we want to compare not the acids themselves, but what we want to compare is their conjugate bases. Okay, and once we look at their conjugate bases, we can compare them to each other and figure out which one is the most stable. So the acid that has the most stable conjugate base, that is going to be the one that is the most acidic. Okay, that is the strongest. And I think there's someone in here. If you want to type a question or ask a question, feel free to. I don't know if you're actually there or not. But when we're looking between these 3, we want to identify our most acidic proton on all of them. Okay, sometimes there can be little tricks with these, but we notice that all of them have the same functional group at the top, known as the carboxylic acid. So we have this, this, and this. So we have these acidic protons throughout all these molecules. And we want to hypothetically say, if these were to act as an acid, and they donate their proton like an acid does, they would end up looking like this in their conjugate base form. Okay, with the minus charge. So we're now introducing this minus charge into the molecule, and we need to compare their stabilities. So if we look at the groups that are coming from the other side of the benzene ring, right? Remember how for the exam 2, you can have these electron donating groups, these electron withdrawing groups, and those are going to impact the benzene ring and its reactivity. Now here, we want to compare these in terms of how donating they are or how withdrawing they are. So the more donating these groups are going to be, right? If something is donating its electron density to something that is already negative, then that's going to be a problem. You're going to be destabilizing the molecule, right? So between all three of these, which the following you think has the most donating group? Yeah, I always like to draw the lone pairs on there. So the one in the middle is going to be the most donating because it's a methoxy group. The oxygen has lone pairs. They can resonate inwards. For that reason, this is an EDG electron donating group, and thus it's destabilizing our conjugate base in comparison to the other two. So of course, this one is going to be the least acidic. So if we had the standard boxes here, put this on do not disturb real quick. So if we had our standard boxes here, of course, the middle one is going to be the least acidic because its conjugate base is the least stable. Now, if we're comparing between the other two, which one is more electron donating between the other two? Okay. So between the other two, the one on the right is going to be more electron donating. Okay, because the oxygen is directly attached. Thus, it can donate via resonance, but the one on the right, you have to look at what's directly attached to the benzene ring, and that is a partially positive carbonyl carbon. Thus, between the two, the one on the right is more donating. Okay, so this is going to be our 2, and then this one is going to be our strongest acid because it's an electron withdrawing group, right? It's going to withdraw some of that electron density, thus delocalizing that negative charge that has been introduced, and therefore it was the strongest acid. So for this one, I would go with 3, 1, 2. All right, so that's for that one. Now let's see what we have going on here. So it wants us to rank the compounds in order of increasing nucleophilic acyl substitution. All right, so nucleophilic acyl substitution is a type of reaction that's going to occur with your carbonyl compounds. And most oftentimes, they're going to have, I mean, in order for it to be nucleophilic acyl substitution, as opposed to nucleophilic addition, you're going to want to have a leaving group connected to that carbonyl that is stable enough on its own where it would be able to be pushed off. So your standard mechanism for this is going to be constant throughout, where you have some sort of nucleophile. It could be cyanide, for example. It could be different things. So let's write that. And this nucleophile is going to go and attack the carbonyl carbon. And then from that, you're going to push the pi bond onto the oxygen. Then it's going to come back down. And when it does so, what happens to this leaving group? It's going to leave. And so you can consider that for all three of these answer choices, okay? Leaving group leave, leaving group leave. So when you're trying to consider which the following is going to react the fastest or be the most reactive, rather, you want to compare their leaving groups. You compare their leaving groups in terms of their stability. the one that has the most stable leaving group means that the original carbonyl was more reactive because when its leaving group leaves, it's more stable. So it's more likely to happen. That reaction is more likely to happen. So let's compare them. So what we want to do, we can just cross this out, put a minus charge on one side, cross that out and put a minus charge. Oopsies. Cross that out and put the minus charge. All right, so now just like in the previous question, you've introduced a negative charge onto the molecule. So in terms of stability, what are we going to look to? We want to focus on the point of difference amongst these three molecules, okay? And we want to see which one of these substituents is going to be the most electron withdrawing and delocalize that negative charge to stabilize the molecule. So the middle one, right, that's the most electron withdrawing group, okay? A strong electron withdrawing group, and for that reason, you're stabilizing the leaving group, and thus the middle one is the one that I would put as 3. Now, comparing amongst the other two, which one of these two is the stronger electron donating group? So your answer should be the one on the left, because it donates via resonance versus the other one donates via the inductive effect. Resonance is a stronger factor. Thus, when this is donating electron density, right, you're destabilizing that leaving group. Therefore, I put this one as the 1, and then this one over here, we're going to put it as 2. And so if you just found out that the middle one was 3, you could have actually knocked out those 3 options and go straight to D. Okay. All right. So let's go on with the next one. So it's asking which of the following compounds will undergo decarboxylation in aqueous acid at H3O+. So this is something that you could see in the reaction section. You could see aqueous acid, so that's going to be it. So 180 degrees Celsius. You're going to see aqueous acid, 100 degrees, 180 degrees Celsius, right? So when you have these conditions, you can have this decarboxylation, and decarboxylation is just like the name sounds. Where you have this release of a carboxyl group and it releases as CO2. All right. So that you have the release of CO2 off of the molecule, and that's going to come from a carboxylic acid. Now, in order for this reaction to occur under these conditions, you're going to want to have another ketone, or rather carbonyl, at the beta position to that carboxylic acid. Okay, so we want to look at that right there, right? So that's a carboxylic acid. We also have a carboxylic acid here. So all of these have a carboxylic acid. Now, of course, if one of them did not even have a carboxylic acid, then this is not going to undergo decarboxylation. So you're looking for that beta keto. Meaning at the beta position, we have a carbonyl. So let's check it out. So if we're looking at the first one, highlighted is our carboxylic acid carbonyl, and then we go alpha to the left, then we go beta one more down. And is there a carbonyl at that beta carbon? No, there's not. So if there's not, then these are not in close enough proximity in order for that mechanism to occur. So for that reason, I would not include one. Okay. Now, and I mean, if you were very sure about that part, I mean, you could knock out and get to your answer. So it's really crazy how the multiple choice, if you study hard and you know some of your stuff, you don't have to know everything, but if you know some of your stuff, then it will help you out with process of elimination here. So looking on to this one in the middle here, what we have is the alpha carbon. We go one down, and that's going to be your beta. And at our beta, we in fact have a carbonyl. We specifically have an ester, right, based upon the molecular formula. So we're gonna want to do two. All right. So I take back what I said. We couldn't rule out all of them, but we could rule out some of them. So then we'll continue on. So we have alpha, we have beta, and of course, right, when we're trying to make that decision between picking actually, I take back what I just said right there. Yeah, you could have based it just off of the first one. Anyway. So let's not worry about that. So basically, you have 2 and 3. These are both going to undergo decarboxylations. Okay. So for that reason, I'm going to go with B instead of C because 3 is included. Okay. I'm not sure if there's a chat room for this. I'll ask this person. Okay. So for number 7, what we have is we want to rank. Okay, thank you so much, Kim. Because I don't see a chat room on my screen, but maybe if oh no, I see it. Kim view to everyone. Awesome. Thank you, Kim. If you want to ask any questions for everybody here, feel free. I commend you for being awake right now. So rank the following compounds in order of increasing acidity, and 3 being the most acidic. So we have these different carbonyl compounds here, and you can notice the difference that some of them have 3 carbonyls, and some of them they have 2, right? One has 2. And you want to make sure that none of these have a carboxylic acid on them, because that is a little bitty trick that Dr. Bean likes to do, where she'll put 2 molecules that are carbonyls, and then there'll be one that's a carboxylic acid, and people will be focusing on the carbonyls, and they will not look to the carboxylic acid. But as the name tells you, carboxylic acid is going to be definitely more acidic. So when we're comparing between these 3, we want to locate our most acidic proton on the molecule, on each one. So let's pick it out for the first one. Where do you think it's going to be? It's going to be right there in between all the carbonyls, because when we look to the conjugate base, it's going to be stabilized, right, via resonance. You're going to be able to draw these 3 resonance structures, okay? Now, when we look at the one in the middle, where would we say the most acidic proton is going to be? It's going to be right there, okay? Now, when we look to the one on the right, we're also going to pick the one that's in between the 2 carbonyls. But as we notice here, the one on the right, it has only 2 carbonyls. It does not have 3. So for that reason, you cannot draw as much resonance. And the resonance structures would look like that. I'll put it in a different color so you can see it a little better. So we can draw these two extra resonance contributors in addition to the one that we currently have. And the other two, we could draw 3. So for that reason, I would automatically want to put the one on the very far right as one it's the least acidic because its conjugate base is not as stable. All right. So now we're going to want to compare between middle one and the one on the very far left. Just want to make sure this is still recording because I'm gonna cry if it's not. Yeah, it's recording. Okay, thank God. So when we're comparing between the other two, we're still comparing the stability of the two. Now, what do we see as the point of difference between the left one and the one in the very middle? So the difference is that the one on the right has this ester to the left of that carbonyl. Now the one on the left just has a straight alkene chain. So it's basically like you have a ketone. You have a ketone here, and you have an ester on the other side, on the other one. Okay, so what we need to think about is the resonance that can be drawn with, like, basically this resonance contributor. This is the important one that's going to make the difference, right? Because that's our point of difference. So we want to laser in on that lone pair right there, okay? And we're saying that this lone pair can resonate and go to the left in order to delocalize the negative charge. Now, when we have this oxygen on the other side, that is going to influence. That's going to have an influence because this oxygen, it can also resonate onto that carbonyl. So that carbonyl is participating in resonance in both ways, okay? So if that carbonyl is participating both ways, right? That means that this lone pair right here, I hope you can see my laser, this lone pair right here, it cannot resonate as much onto the carbonyl because the carbonyl's attention is getting pulled this direction with this oxygen, as well as this direction over here with the lone pair. So it's like 50-50 both ways, okay? So for that reason, this lone pair in the middle cannot resonate as much, cannot delocalize its charge as much, and for that reason, this one, the conjugate base is not going to be as stable. So I'll put that one as 2. Versus we'll compare over here to this one, and what we have is this lone pair that can resonate to the left, go on to the carbonyl carbon, right? Form that O-, and 100% of that donation is going from this lone pair right here. 100% it can go here, as opposed to if we had the oxygen here that is taking up the attention of that carbonyl. Okay, so for that reason, this can delocalize its charge more. And whenever you have more delocalization of that negative charge that has been introduced into the molecule, that is what can stabilize the molecule. So for that reason, I would go with 3, 2, 1 here. Okay, and that's gonna match with the answer choice B. Okay. A lot of students, this can trick up a lot of students. They see that middle compound, they say, oh, the oxygen on the left can also resonate. Oh, isn't resonance good? It's a good thing, it's stabilizing, but not in this particular instance, okay? It's taking up the attention of that carbonyl. Any questions about that? To my one student. Alrighty. So here it says rank the following compounds in order of increasing rate of nucleophilic acyl substitution. So we previously had a question that involve nucleophilic acyl substitution, right? So when we're talking about that question, over there, we considered the stability of the leaving group. And you can consider the stability of the leaving group as well as the partial positive charge of the carbonyl in addition to steric hindrance, all right? But we'll talk about it as we go through the example here. So right away, what I would say for these is just identify your functional group and ask yourself, what's the functional group for the one on the left? That's going to be an ester. And then the one in the middle, what do we have? We have an amide. And then on the one on the very far right, we also have an amide. So you're going to definitely want to be very comfortable with the ranking of the reactivity of these carboxylic acid derivatives, all right? So at the very top of our food chain, and I think in the exam 2 multiple choice that Danny and Kevin did, they did a really great job. I think Danny listed them out. I don't know if he did them in terms of reactivity or just for nomenclature, but acid chloride is going to be at the top, okay? Then we're going to have anhydride, and then I believe ester is going to come next, and then we're going to have amide, okay? And I'm not going to include the nitriles here, okay? They're kind of in their own category. So when we're comparing between these two, I just kind of said it, our amide is the most stable out of all of these, right? And so our ester, right away, our ester is going to be the most reactive. So we're going to put 3. All right, and not even look any further just by knowing that trend. Now, and that's because its leaving group is the most stable when you have a minus charge. When you have a minus charge on oxygen versus minus charge on the nitrogen in the amide, okay? Now, we'll compare between the two amides. And what is our point of difference here between the two amides? So remember, the nucleophile is going to go and attack that carbonyl carbon, okay? And so when it's trying to make its way there, when you have the same functional group, right, amide versus amide, so we're comparing not apples to oranges, we're comparing apples to apples. Same group, then we can look to steric hindrance. As a factor here. And so which one between these two, which one do you think is going to have more crowding in the site of the carbonyl? I would say it's going to be the one that has these two methyl groups here, versus the other one does not have them there. It has them on the other side. But this is the side of the attack. So that's the reason why I would go with that one right there being less reactive in the middle. So put that one as number 1. And I'll put that one. And then I'll put that one as number 2 over there. So I go with 3, 1, 2. All right. So now we're getting into some reactions. And here it wants us to choose the final major product for the sequence of reactions below. Alrighty. So what's the functional group? What's the molecule that we're starting with? What is that? You got to think. Right. So this is an acid chloride. And acid chlorides, remember, like I said, the acid chlorides are the top of the food chain in terms of reactivity. Okay. Not nomenclature, but reactivity. So then when we start with our number 1, what we have going on here is we have this similar to lithium aluminum hydride, Layla, but what it has is these 3 terbietoxy groups coming off of the aluminum. So look at it like this. Look at the structure for this. You see how bulky this group is? So on top of the fact that it's bulky, it's providing one source or one equivalent of the hydride. Hydride is minus charge on the, or a hydrogen with a lone pair on it, okay? And so that is going to go, if I use my laser point, that is going to go and attack right there, come back down. You guys seen this several times. It's going to push the chlorine off there. And what you get as a result of that is you get an aldehyde. Right, because you're providing that hydride there, and that's what we're gonna see there. So what's special about this is it's selective for the acid chloride, so it's only gonna react with the acid chloride, not with the carboxylic acid. And on top of that, you're providing this one equivalent of the hydride, and it's going to happen once, so you're not going to have it attack again, okay, due to that reason, and you're going to result with the aldehyde. Alrighty. Okay, so number 2 seems as though this is one of those newer reactions. This is coming from the chapter 22, and you have ethoxide, and then of course it's in its solvent, as well as you have heat, okay? And so what's going to happen here is we're going to have, let me draw out the ethoxide. OET. Yeah. So this is going to be a strong base, right? Running out of time. We've removed the 40-minute time limit on your group meeting. Okay. Oh, I forgot that it does that. Okay. I don't know how much time I have left. Oh, question. Why wouldn't it attack the top? Oh, okay. So you're talking about number 9? Ooh. Okay, so for number 8, whenever you have the nucleophilic acyl substitution, you're gonna, the side of attack for your nucleophile is always gonna be that carbonyl carbon. And the reason for that is because you have a partial positive charge on that carbonyl carbon. Because think about the resonance structure that we can draw, where that pi bond goes onto the oxygen, and that would give a positive charge right there. Yeah, good question. And it said that I am supposed to only have 40 minutes for this. I'm not sure how long it's going to go, but just let me know if you're still there. Let me know if it stops, okay? Or if I think it starts counting down from a certain number, and if it starts doing that, then I'll just have to stop and restart again. Okay. Cool. So what we have going on here is we have this aldehyde, right? And when you have the strong base, this proton over here to the left is going to be extra acidic because you have a carbonyl carbon right beside it. Okay. And so that's going to get deprotonated. So I'll go with that. And we're removing one of those protons, one of these. And you can draw like the different resonance structure for this, what's going to be called an enolate, but here we'll just keep it simple by putting the lone pair on the carbon. Okay. So what we formed here is we formed a strong nucleophile. Okay. And this strong nucleophile, what can happen here is this can go and attack one of its own molecules. When I say that, let me draw out, not these, another one. All right. So I'm going to draw another one of the reactants that we had in after step number 1. I'll draw another one like that, and there's going to be a side of attack on that. So where you think would be the side of attack? It's going to be that partially positive carbonyl carbon, just like in the previous question. So this can go and attack right there and push those electrons onto the oxygen. And when it does so, right, we can draw, let me draw the molecule we had right up here. That. So I'm trying to draw this piece. So I'll put the C and the H. Now the lone pair went into forming the bond. Right. And when it did, it went to form the bond to the carbonyl carbon of the other one. I'll just write the aldehyde part right here first. And then this is the bond that's worth forming, okay? And that's the one that's going to get formed to the carbon of the carbonyl, right? And of course, that resulted in an O minus in addition to a hydrogen. And then also coming from that carbon, we're going to have the remaining pieces, so the CH2, as well as that cyclohexyl. So after that happens, we're going to have a protonation, and the protonation of that, I'll put the lone pairs. The protonation of this is going to happen via the use of the solvent. So you have that ETOH, right? That was a result of that original deprotonation that we had. And that is what's going to protonate that, okay? If you're wondering. Okay. So what we get here is this special alpha, beta, I guess you could call it beta hydroxy or beta alcohol, or a beta hydroxy ketone, I believe is what they can refer to it as. And you just have a hydroxy group coming off of the beta carbon of that, whatever your carbonyl is, okay? So just looking at my options here, seeing that one of the options does not even have the 2 rings on there, right away I would knock that one out, okay? And then the number 4 isn't making much sense just because it has like this acetal structure. Yeah, I mean, that one doesn't have the cyclohexyl either, 2 of them. So I guess with that one, she's trying to confuse you guys. I'm not really sure, but it definitely isn't going to be one of those 2. Now, looking at the other 2, 3 and 2, they both look promising. Okay, they both look promising, but the thing is that they have this double bond there. Okay, and so we want to be really careful of the placement of that double bond. And what we have here is heat. Remember, up here we have heat. And so what's special about the heat is if you heat this up, then you can force a elimination to happen here. Just like remember in Oreo 1 when we study E2 and E1, where we're forming what functional group? We're forming an alkene. And so we can have an elimination happen right here in the molecule that we drew. We can have an elimination happen between right here. So basically between the carbon that has the hydroxy group as well as the carbon up here that has a hydrogen. And the reason why this is going to occur, I mean, hydroxide is a terrible leaving group. I mean, for this to leave, right, you would be forming hydroxide OH minus. And isn't OH minus an incredibly strong base? I mean, that's incredibly unstable. And so that's something that can be alarming. However, when we look at our product, I hope we're going to see something that is going to give it this special stability and would help this out to occur. Okay, and the mechanism is going to be a little bit different. It's not just going to be your ordinary, deprotonation and this bond comes here and then hydroxide comes. It's going to be a little bit different than that. There's going to be some help from somewhere else on the molecule in order for a hydroxide to leave like that. That's what Dr. Bean will discuss. But in terms of getting to our answer here, we're going to have the aldehyde. That carbon is now going to have the loss, the elimination, right, of the hydrogen as well as the OH group. So we're still going to have this. And now we're going to have a double bond to that carbon with a hydrogen with the benzyl as such. So we're going to now have a alpha beta double bond, right? You start at that alpha carbon, which is the one to the left of the carbonyl. So this is different than with alcohols. Alcohols, the alpha carbon is the carbon that's attached to the alcohol, the hydroxy group. Here is the carbon that's one over from the carbonyl. That's your alpha carbon, and then you go down, and that's going to be your beta. One of the students is asking me a question. Okay. So that's what we're going to end up getting from there. And so we want to look for our answer choice. Which answer choice is that going to be? Yeah, so we got to be really careful here. So we have a CH2 connected to a CH, which is going to have, okay, so it's not going to be that one. It's going to be this one. There's a lot of marking. I apologize for that. We just want to make sure that we have the aldehyde. Here, I'll use this. The aldehyde part, then we go to a carbon that has this over here, and then we continue to the CH, as well as it's going to also have the benzyl group. All right, so that's how we're going to get the number 2. So we're going to get, see. All right. So this is new. This is from chapter 22. So if you have any questions, please ask. Alrighty. So we'll continue on. So it says choose the final major product for a sequence of reactions below. So very similar idea here, where we have NaOET, so we have that ethoxide, and that's going to perform a deprotonation. And where is that going to deprotonate on our molecule? I'm going to make my pen a little smaller. So that's going to deprotonate our most acidic proton on our molecule. Alrighty. But these, they can get really tricky. So honestly, I recommend drawing this stuff out. I mean, of course, if you practice it and you get really good at it, you don't have to. But it's very easy to miss carbons with these. Okay. So we have the deprotonation there, and that's going to form this strong nucleophile, right? Because that is a carbon on, that is a negative charge on a carbon still. All right. So then what we have is we have this CH3, 2 CH2, CH2. So we have this alkyl bromide here. And so whenever you have an alkyl halide and you have a strong nucleophile, what's going to happen? We're going to have an SN2 reaction. And just for organization's sake, we're going to take this lone pair. It's going to go and attack this CH2, the partially positive one, and then it's going to push off the bromine. Okay, so that's the connection that we're making right now. So I'm going to put our nucleophile, boom, boom, just like that. And now we're going to have formed a new bond, and that new bond is going to be this one right here. All right, so this is an alpha alkylation. So at the alpha carbon, we're alkylating it. We're actually forming carbon-carbon bonds, which is very, very useful to use. All right, so we're going to want to add basically a CH2, a CH2, and then to that CH2, we're going to have I think there may be a typo here. It goes CH2, CH2, and then it has 2 methyl groups. But in order to have 2 methyl groups, it would have to be a CH. You see what I mean? Like right here. You can't have 2, because if you do, then it would be like, it would look like this. Kim, are you there? Do you see what I'm talking about? Yeah. That could be a typo. We'll go to the answer choices and see what's going on with the answer choices. We can keep it as one. I guess we can keep it as this for now. I'm not sure. We can keep it as this, and we'll see what happens. Okay. So after we have that alkylation, looking at the answer choices.
Morning.
Hello. Oh, is that Elsa?
Yes.
Hi, Elsa. How are you?
Good. How are you?
I'm doing great. We're going through the exam, and so I was just asking if you wanted to join in. Um, we're recording it for everybody.
Mm.
But we got to number 10, and it seems as though there might be a typo in the question.
Oh, is this the multiple choice one that she gave us?
Mm-hmm.
Oh, okay.
Yeah. So in number 10, we're looking at it, and it says that there's supposed to be a CH2, then a CH3, like two CH3 groups, but that can't necessarily be the case because you'd have a carbon with
Mm.
more than 4 bonds. So we'll keep it like that, and we'll just continue on with it, okay? And
Okay.
then for step number 3, what we have is that H3O plus and 180 degrees Celsius. All right. So we want to see how that's going to influence this molecule. So we have, what are our functional groups? We have an ester, and then we have this. So I'll highlight the ester, as well as we have this carbonyl over there, right? And it's not going to really do anything to our carbonyl per se, but to our ester, when we have H3O plus and 180 degrees Celsius, something can happen there. And what's going to happen there is we're going to have some hydrolysis. We're going to hydrolyze that ester. And what are we going to form as a result?
Then carboxylic acid? I don't know.
Yeah, awesome. Feel free to chime in. I mean, it makes it, honestly, I started the recording by myself at like 8 this morning, and I was so bored. Like, I was literally talking to myself, and I was just bored to death. I was like, I don't know how I'm going to get through this. And spend
Yeah,
like 2 hours on this thing or whatever. I was like, I have to, like, hopefully one student, I need just one student, one person with me that it's definitely a lot better. That's why
yeah,
I thought you
that's
said.
my bad. My alarm doesn't ring until like 9.
Oh no, normally mine rings a lot later than that, so you're good. But look, we have, I think we have Kim here as well,
Hello,
so
Kim.
that's good. And so,
And
so
then
what we
like
have
my
here is,
alarm rang and I was like, oh, I was like, let me check it out.
yeah. So what we had here was the hydrolysis of that ester, and we formed a carboxylic acid. All right.
Mhm.
And when we do that, we have this special type of functional group where we have a carboxylic acid, and then we move over to the beta carbon. So this is kind of like one of the earlier questions that we were doing, that whenever you have this beta keto in relative to the carboxylic acid. So whenever you have at the beta carbon, you have a carbonyl, and you have H3O plus at 180 degrees. What's going to happen is you're going to have this decarboxylation, which means that this carboxyl group is going to be able to leave. It's going to float away, and it's just going to be replaced there with a hydrogen. So in our answer choice, we want to look for the one that looks like this, but that carboxyl group is replaced with a hydrogen.
Mm. I'm pretty sure we did just learn this like yesterday.
Yeah, this
Pretty
was in
sure.
the lecture yesterday. And
Yes.
so let's see which one that would be. So we want to have one that for sure it doesn't have a carboxylic acid anymore.
Okay.
So for sure that, like, if we want to do the process of elimination,
Not that one.
it's not going to be that one. So that's what we would have before the carboxylation, right? That's what we had after what I have on number 3.
Mm-hmm.
And then number 4 has an ester. So we don't have an ester in ours.
Mm-hmm.
And then in number 1, we have an ester and we have a ketone. which is not what we have in ours. So then in number 3, that should be what we're left off with here. Because we have 1, 2, which is
1, 2,
1,
3.
Yeah, count it out. And then we lost the carboxylic acid right here.
2, 3, 4.
So that got replaced. And so I guess that there was a typo with this. Or I mean, I'll mention it to her and see what was meant, but I think that was meant to be a
Isopropyl?
a CH2. I think it was meant to be a CH2 with another
an extra
CH2,
one.
and then I guess it's missing a CH.
1, 2.
Like, let me rewrite it. If we were to have had
CH2, CH2, and then yeah, it would be an isopropyl, right? CH2, or oh no, but it has extra CH2.
like so the issue was over here where what we had was on number 2, it's giving us a CH3 in parentheses with 2 and a CH2, right? But if you try to write that out,
2, 3, 4.
you see how there's a small problem here because we have, look how many bonds there are to the carbon.
Ah, I see.
Like, so that's pentavalent. So I think, and we'll definitely mention this to her just to be sure, but I think that it's supposed to be that. Because if it was that, then we would indeed get number 3 as an answer choice.
Yes.
You see what I'm saying?
Yes. Okay.
I'll just go ahead and replace that real quick. So you CH. Okay. So we'll replace it with that just for now.
Oh, she did.
She did what?
This is the one that she was talking about, that there is a typo. I have it on my screen right now. It says CH3, it says CH2, carbon, an extra carbon, and then CH3 2 times.
Oh, okay. Did she post a new copy?
Yes.
Oh, okay. Okay,
So
awesome. I'm glad we
it's
got it figured out.
CH2, and then a carbon, and then 2 CH3s.
Okay, perfect.
It's still probably, is that still right? Oh, yes, because it's attached to the carbon, and then yes, that would be correct, yes.
Yeah, okay, someone must have mentioned it to her. That's good. Okay, awesome. So then we're going to want to go with 3.
1, right?
This one right here.
I mean, sorry, 3.
Yeah, let me highlight it. Yeah, there's just there's not a lot of space on this. I should have added a page or 2. But yeah, so we were going to go with 3. So A. Okay. Alrighty, so let's see what we have here. And I might add a page because this is, or no, I'll just work it up. Okay, so for this one, we're supposed to choose the final major product for the sequence below. Okay, so we have lithium aluminum hydride, and it's in excess, right? So that's a little hint towards something. So what do you think is going to happen here? We have these 2 functional groups. We have an amide And we have an ester.
Well, I know, isn't it a strong reducing agent?
Yes, it's a very strong reducing agent,
So,
and so it's definitely going to react with the ester. We learned that from Formula 1. Huh?
Would it end up breaking the bond?
Yeah, it's going to break that bond, and you're going to introduce a source of hydride right there at the carbonyl carbon. Okay, so you're going to end up breaking it up. It's going to come back down just to show the pseudo mechanism. So you're going to break that ring up, and so we'll just deal with the ester part first, and then we'll talk about the amide. Okay, so that's the amide is still intact, and then what we're going to have is at that carbonyl carbon, it's going to become an OH. It's going to be reduced to an alcohol. Okay, and then the other piece, remember it broke off, that O minus that broke to the other side. So now we're also going to have an alcohol. So we have these two arms coming off, okay? And then in addition to that, we have the amide. And so to deal with the amide, like you said, it's a strong reducing agent. So it's going to reduce the amide as well, but it's going to reduce it in a little bit of a different way. What do you think? Any idea?
Is it going to add an extra H?
So it is going to add H's. I mean, just by knowing it's a reducing agent, so you're going to add H's. You're going to add H's. This is a new one, a relatively new one. So you're going to add
have
two
to break
H's
again?
to that carbonyl carbon, basically. And so you're going to reduce it, and it's very different because you're going to reduce it all the way to a CH2.
Oh, there you go. That's what it is. We did this yesterday too. In recitation.
Oh, yes, yeah. So it's going to reduce it all the way to a CH2. And so that's what we're going to get from step number 1. And 2, I guess, yeah. Step number 1 and 2, because the step number 2, the H3O plus is going to be responsible for protonating these guys as well. Okay.
So the carbonyl becomes CH2?
Yes, exactly. So like right here.
Perfect. Thank you.
Of course. So now moving forward to step 3, let's see what we have. So in step 3, we have these two alcohols. We have an amine over there on the left, and then we have this acid chloride. And again, this is given in excess. So what do you think could happen between an acid chloride and the alcohols? Whenever you see,
very reactive, so it's probably gonna react with the carbonyl and have a good leaving group.
Yeah, so they're very reactive. They're at the top, and so you'll notice a trend that whenever you see you'll see commonly like the acid chlorides can react with a lot of things, a lot of different things, and you can see the alcohols can react with a bunch of these as well. And it's just a common trend where you're gonna just smush the two together. So you probably you don't want to have to just memorize them separately. Just relate them to each other, in that if you have this carbonyl-like structure, you just are going to attach that straight to the oxygen of your alcohol. And like you said, the chlorine is going to leave. That's a really good thing to note as well. So we will just put, I'll copy this if I can. I'm gonna react with that. So we make that connection there. as well as with the other side. Okay, so that's what's going to happen on the sides with the alcohols. All right. Now, is anything going to happen, you think, to the amine?
Well, doesn't it also have a lone pair? That, oh wait, it has 3 bonds already.
So it has 3 bonds, and so that does mean that it has a lone pair. Now, if you're unsure, we could even look to our answer choices and see.
It looks like it is gonna happen because all of
Yeah.
them.
Yeah, 100%. So that's actually really interesting how the multiple choice can help you out if you just know part of it. So even looking at number 2, we haven't broken up the ring at all. So we're going to cross that out. And then for number 4, we have everything so far except for the left piece. And then for number 3, we haven't even opened the ring at all, right?
Mhm.
So we can cross that out. And then over here, oh, I'm not even sure how that would happen. This right here, I don't know how that would happen. So definitely, I like what you were saying. I would also say that you have the lone pair on that, and so that's going to do a very similar thing, and it's going to react with the acid chloride. Remember, we were doing some mechanism, or not mechanism, synthesis, and whenever we want to form an amide bond, we typically use an amine, and we use a acid chloride, and we smush them together. So that's exactly what we're going to want to do here. Okay, so we're going to have that connection. So we take the carbonyl piece of that acid chloride, and we just combine it right there. All right.
Yay.
Yay. So I do
it. Oh, you can hear my whispers too. I'm really loud.
That yay was so fake.
Mine?
So
No, it was real. What? You know, sometimes I think that I sound like I'm being sarcastic, but I'm actually being honest.
Completely serious. No, me too. Me too. I'm actually super pumped right now.
Same.
All right. So now we can keep going. So choose the major product for the sequence of reactions below. All right. So we have an amide, and then we have this SOCl2 and POCl3. All right. So do you remember my little stupid mnemonic from recitation the other day with the SOCl2?
Oh no. But I know, isn't it going to change it to Cl? No.
What's it gonna do to the amide? Well, that means my mnemonic was probably too stupid to.
I don't remember.
But basically, you have SOCl2. Oh, maybe you weren't there for that day. But you have SOCl2, and so if you say it in a British accent, it sounds like you're saying soak, right? Soaker. So you're gonna soak up all the water.
Mm-hmm.
You're gonna soak up all the water. So this is a dehydration reaction.
Mm-hmm.
And so if you can remember soak up the water, you can remember that it's dehydration and that you're having the removal of water, which is just H2O. And what are we going to get? What functional group has a carbon and a nitrogen?
A nitrile group.
Yeah. So you soak up the water.
Ah, I like that.
Yeah. So then we end up with a nitrile group right there. All right, so then we have basic conditions and we have very high heat. And so I want you guys, again, to relate these to the other carboxylic acid derivatives for whenever you have high heat and base, or if you have high heat and H3O+, right? If you have either of those two, right, it's just acid catalyzed conditions versus basic catalyzed conditions. And you're gonna do the same thing across the board. It's gonna do hydrolysis, where you're gonna hydrolyze that group and you convert it back to the carboxylic acid.
Mm.
So remember, these are called carboxylic acid derivatives for a reason. Right? You can easily go back to the carboxylic acid if you just put it in water and turn up the temperature and have it in base catalyzed or acidic conditions. So you take that carbon, and that carbon is going to become now a carboxylic acid, okay? And now we have step 3. And so for step 3, what do we have going on? We have an acid chloride. So how is an acid chloride, you think, going to react with a carboxylic acid?
That's a good question. Because well, the OH is there. So will it? I don't know.
So this is another one of those ones where I really want you guys to, instead of trying to like memorize them, just memorize. I mean, look at the structures and
Is it gonna
think
do
about what
an
in the structure can
anhydride
remind you
thing?
of what happens. You have this carboxylic acid with this OH group. You have this acid chloride with its Cl group. And so if you just smush these together, of course, including the oxygen, if you smush them together, then which type of functional group would we get? I'll put it to the side here.
I thought that was an ester, but I don't think that's an ester.
Close. Oh, Kim says,
An
haha.
anhydride is something different.
She's laughing at us also.
Who?
Kim, I guess we're funny.
Oh.
We're entertaining. So it's almost an ester. So an ester would just be this portion.
Mm-hmm.
But when we have the two come together, now we have this anhydride.
Oh, okay, I was right. I wasn't sure. I forget.
Yeah.
I said anhydride, but then I was like, I don't know. Maybe I'm wrong.
So no, you're right. Go with your instinct. So it's an anhydride because in order to create an anhydride, you would have to have the removal of water. So it's anhydrous. So you're removing water. The name can help you out to remember it. So what answer choice would we go with if that's the case?
It would be I
Yeah.
or 1.
It would be this one.
Mm-hmm.
So number 1. So we're going to put it as B. All right. Yeah, I'm just going to. All right. Oh, and I think Wally is here too. Hi, Wally. So for the next one, it wants us to choose the major product for a sequence of reactions below. And what we see at the beginning there, that is our Grignard reagent, right? So how is our Grignard reagent going to react with carbon dioxide?
Oh, that does the whole situation where it hits that and then it gives you a carboxylate, I think, and then you have the H3O and then you protonate it, I think.
Yeah, very good. Yeah, you're right on the money. So you have this Grignard, it's a strong nucleophile. You have this weak electrophile, which is a carbon dioxide with that.
Oh, so you would get a carboxylic acid, right?
Mm-hmm. Yeah. So you're gonna have that connection there. So for this one, I mean, you probably wouldn't even have to write out too much, to be honest. I mean, you could even just go off of looking at the answer choices if you know what step 3 does.
You know, we did
the hard
step
part.
3 too, and I.
Huh?
Oh, I was saying we did this yesterday too.
Mm-hmm. We did this one yesterday in the recitation. So we'll just put 1 and 2 together since you already said it, that you're basically going to create that carboxyl group, and then you're going to have the protonation with H3O plus, and so we go to the carboxylic acid. Okay, and then we have this diazomethane. And what we mentioned yesterday is it's going to give us a very particular type of ester, and that's going to be a methyl ester, right? So it's just going to be, we're going to form an ester, and it's going to have a methoxy group coming off of it, okay? And you can use to remember that fact just based upon the fact that you only have one carbon in that diazomethane, right? There's not two, there's not more than that, right? There's only one. So that's where it's coming from. It's coming straight from that. Okay. It looks like. That's a resonance structure for it right there. So you can see its nucleophilic character as well, okay? That's where the lone pair right there. Okay, so there's gonna be an attack of some sort. Okay, so what we have going on is we're just gonna go straight, or you know what? We can go straight to the answer choice.
Yes, I think there's only one on there.
Yeah, because there's no amine involved. See, I think she's trying to confuse you with the fact that it has nitrogen. You see that?
Yes.
But the nitrogen is going to be released as nitrogen gas, and that's
why it's a good reaction, right?
Yeah, exactly. Whenever you release as something that's gas in the form of in its gaseous state, you're increasing the entropy. And so that is very favorable to increase the disorder. And so that's why we would go with 3. So if you knew that fact, then you could even deduce, it's not involving the nitrogen at all, it's released, then let's go with the one that doesn't have the nitrogen, okay? Alrighty. Okay, so select the sequence of reactions that will convert the starting material. I just want to make sure this is still recording. Okay, cool. And convert the starting material to the product and the best yield. So what we have going on here, we have this cyano group, we have a ketone, and what is different between these two?
No, we don't have a cyano. We've gotten it. Is it reduced?
Yeah, exactly. It's gotten reduced, and we actually did this I think we did this in a previous question on this worksheet where we had the reduction of a cyano, and
so we have to do a protective group and then.
Yeah, so notice, good job. So notice how nothing happened to the other group, right? So because nothing happened to the other group, that's your clue. We have to have a protecting group, because if you're going to use a reducing agent, I mean, do any of you guys know what the reducing agent might be in order to do this?
Has to be a strong one for, right? Oh wait, there's only a specific one that she gave us, which I think it's the lithium aluminum. For nitriles, I think.
Yeah,
specifically,
for sure. And even if you were unsure, I mean, remember, this is multiple choice, right?
So you can already
because there is a different reagent that you could use. Huh?
Oh, I said there's already 2 answer choices that you could take.
Yeah, for sure. Like you see in B that we have an oxidizing agent, so that can't be even the case. So we could knock that out. And the other one is taking it to a carboxylic acid. The other one, I just don't even, yeah, it'd be trying to take the nitrile to a carboxylic acid and then reacting that with NH3 to create an amide. And then, yeah, we got stopped there. So even if you were unsure, like you said, right, you see two that have the lithium aluminum hydride, so you can go straight, just go with that, right? But there is a different reagent you can use. You could use like a H2 with a metal, with a solid metal, but I like using the lithium aluminum hydride better. Since we already know it, we might as well use it. So we're going to want to reduce it. Now our options are we going to want to pick between A or C?
C, because we need to protect the
ketone. Yes, perfect. So we're going to want to protect it. You said it right. So we have this diethylene glycol, and that's going to protect our ketone. so that we don't, when we hit it with the lithium aluminium hydride, we're not going to also reduce the ketone, because what would the ketone be reduced to?
Carboxylic acid.
Reduce.
Oh, I'm sorry, reduced to.
Yeah, you're okay. Yeah,
It'd be
okay.
an
You
alcohol.
said it so confidently.
I'm dead.
It's okay. It's okay. I called on you early in the morning, so you're gonna reduce it to a alcohol, right? If you use that there, so you definitely want to have the protecting group already on there, and not A.
Mm-hmm.
Okay, and then after we do that, we do the lithium aluminium hydride. That's going to reduce the nitrile to the primary amine. This only works on primary amines, okay? And then when you do H3O plus, that's going to hydrolyze our protecting group, as well as continue with the last part of that reduction. So that's how you would get back to the ketone.
So the lithium aluminum hydride is only going to work with primary nitriles? Oh, wait, but isn't that the only kind that you can have anyways?
Yeah, exactly. So you're only going to, I should have said, you're only going to get primary amines. I should have said it that way. Does that make sense?
Oh, okay. Yes.
Yeah. Because then, yeah, just by by default, the structure of a nitrile.
Sorry, I'm like you said. I'm still low key a little.
No, it's okay. It's okay. I thank you for being here. So for 15,
thank you for having me.
It says to select the sequence of reactions that will convert the starting material to the product in best yield. Okay, so this is just like a small pseudo synthesis question here. And what we have is we start with an aldehyde. And what do we see the difference between our starting material and our final product?
We have an alpha, right? We added an alkyl group in the alpha position, right?
Yeah, good job. Yeah, 100%. We just have an alpha alkylation. And so that's the reactions that you guys learned yesterday in the lecture. And so that specific alpha hydrogen, this one right here, is a little bit more acidic. Why do you think it would be a little bit more acidic?
Because of the oxygen, right? It's pulling or induction. I don't remember what it's called.
So it definitely is involving the oxygen, and it's involving the oxygen in the sense that if you look at the conjugate base, let's say it got deprotonated, now we can have some resonance, right? So we can have resonance with its conjugate base, so the pK is going to be a little bit lower now that we have that carbonyl right next to it. It's going to be a little bit more acidic. So if we use a strong base, we can deprotonate that. All right. And so there's going to be these different options. And this is honestly, in my opinion, the hardest part of all of Orgo. From the very beginning, from when you guys were learning, like, what is a carbocation to now, I honestly, like, for me, I found this chapter 22 to be the most demanding and hard to keep track of everything. Now, if we were to, let's try this by looking out at our options and seeing what we have. So the first one, it gives us this LDA. And LDA, it stands for, I believe, lithium diisopropyl amide. And so it has the word amide in there. And remember, we know an amide, it looks like this, right? But also, if you have a nitrogen with a full minus charge like that, that is also an amide. Not a lot of people know that. So with this base here, when we have this, so we said it was diisopropyl. So we're going to have these two isopropyl groups, and they're going to be connected to the nitrogen. And we have a minus charge on that nitrogen. All right. So that's a strong base. Right?
But isn't it also a big, bulky base?
Yes. And so the fact that it's bulky is also very important. So it's a bulky base, and it's a strong one too. okay? And so that could deprotonate oftentimes next to a ketone. For example, if you had this.
Are you drawing something by any chance?
Oh, is it not moving?
No, I don't know. I don't know where you were drawing. We just see the 15.
Oh, okay. Oh, I'm seeing. Yeah, I'm looking at my. I have it like connected to my laptop, and on my laptop, I don't see the screen moving. It did this earlier. Let me stop the share, and then restart the share. So share screen, and then iPad. So let me know if you can see it now.
Oh, yes.
Am I moving?
Yes.
Okay, yeah. So I don't think you guys saw that I was drawing like the amide or the bulky base or this. But this is what I was drawing on the right over here, okay?
Mm-hmm.
Let me go back to the meeting. Okay, yeah. So what I was drawing on the right over there is the bulky base, the LDA, as well as a ketone. So this bulky base can go and deprotonate this and form that enolate that they call it, enolate. And I mean, I'll just show you guys the resonance structure that. So let's say it deprotonated that hydrogen, right? We can do that there, okay? And then we also have this sodium ethoxide, which is also a strong base, not as strong, but what it can do is it can also deprotonate, but it's not bulky, okay? And this can deprotonate whenever you have this type of proton in the middle, right, of two carbonyls. You can imagine that's going to be more acidic than if you had just one carbonyl, right?
Mm-hmm.
So sodium ethoxide can deprotonate those. You most commonly see it used with those.
Oh, is that one better just because that one, would this be considered more steric hindered if we have two ketones next to it? Or does that make a difference?
So it wouldn't necessarily be more sterically hindered. I would say that in the middle of those two carbonyls, right? Whenever you have a proton there, because there's two carbonyls, they can the conjugate base, that carbanion, can resonate. That lone pair can resonate both directions, right?
Mm-hmm.
So wouldn't that stabilize the conjugate base? So it's
Yes.
so because it's the conjugate base is a little bit more stable, because there's, well, I wouldn't say a little bit, a good amount more stable. That's a more acidic proton.
Okay,
And
yes.
because it's more acidic, you don't have to use as strong of a base.
Okay.
Remember, if you have a minus charge on a nitrogen, nitrogen is not as electronegative as oxygen.
Mm-hmm.
So a nitrogen with a full minus charge is going to be a stronger base than an oxygen with a minus charge.
Yes.
So that's why you got to use something so strong for when you have only one carbonyl there. Right?
Okay.
That acidic proton. Does that make sense?
Yes.
Versus when you have the two carbonyls, that proton's going to be a little bit more acidic, and so you can use a weaker base like sodium ethoxide in order to deprotonate it. Okay, and but in this particular question, we have an aldehyde. Okay, so the end all be all, the best way, the ideal way to do this for an aldehyde would be doing a particular reaction known as Stork synthesis. I think the guy's name was Stork.
Oh, yeah. This was, I think, the last part of yesterday's lecture.
Okay, yeah. So for LDA, it's not going to be used for the aldehydes, okay? Because despite the fact that that base is so bulky, an aldehyde, there's not a lot of steric hindrance. It only has an itty bitty hydrogen from one side. So sometimes you can have the attack of the carbonyl carbon instead of the deprotonation. So that's why it's not as ideal to use LDA if you want to 100% ensure the alkylation, because aldehydes have less steric hindrance. So even though the LDA is so bulky, you could get some attack of the carbonyl instead. And so for that reason, we're going to want to knock it out. The LDA should be for ketones, not for aldehydes. Okay. And then the sodium ethoxide, I would say that is more ideal for when you have the two carbonyls and you want to deprotonate the proton in between. So I'll cross that one out. And then we come across this Stork synthesis. And what's really good about this, what you do is you kind of take advantage of the fact that if you react, the reaction between a carbonyl, you take advantage of the reaction between a carbonyl, which could be an aldehyde or a ketone, and the fact that they react with a secondary amine and the way in which they react with a secondary amine. So let me ask, how would an aldehyde react with a secondary amine?
That's a good question.
This is from a little while ago. So it's from a little while ago. It's from the aldehyde and ketone. That might be chapter 18, I believe. So what you're gonna get whenever you have an aldehyde, secondary amine, you're gonna get an enamine.
Okay.
That looks like this. Let me make sure my carbon's 1, 2, 3, 4, 5. Yeah. And then you're going to have those two, of course, whatever was coming off of that, it doesn't really matter, honestly, because the amine this is going to get lost in the reaction. But you have 1, 2 carbons, right? Because it's CH2, CH3. Then we have 1, 2 carbons. Okay, so that's now going to be connected there. And what we have from that, we still have a lone pair on that nitrogen, right? Let me draw it closer down. Okay, and then what's going to happen when we created the enamine. So what's going to happen when we input this alkyl halide, we're going to have this come down. I wish my font wasn't so big. I can just use the this is going to come down. So you have this neighboring atom participation, and then it's going to propagate this pi bond to act as a nucleophile and go and attack at this electrophilic carbon. And that's going to push off the bromine. So now we're having that alkylation of, do you see where I'm going with this?
Yes.
So we have that alkylation of the CH3, CH2, CH2, which is what we actually see right there. Okay. And when that happens, so if I were to, let's say the lone pair, remember the lone pair came down, this went and attacked, so we got the alkylation now, and then since the lone pair came down, that's where it's now present. And what's our charge on the nitrogen?
Positive.
Yeah, positive. So now we input this H3O plus, and at the very end of this reaction of creating once you create an enamine and you have this iminium, it's called the iminium ion. When you put H3O plus there, you're gonna be able to send it back to the carbonyl, right? Remember, when you're trying to create the enamine, you want to put non-aqueous acid. And so whenever you put aqueous acid, you're going to send this back to the carbonyl. So you just basically replace that nitrogen And this is at some point in the mechanism going to come off, and you replace that with the oxygen of the carbonyl. Yeah.
I should really go over my chapter 18. I just
Chapter
remember the
18.
most recent parts now. Bye,
Yeah.
love you.
Yeah, chapter 18, I would say the most important reactions from that one, like just remembering from the top of my head. I mean, I would say it's those with the secondary amine and the primary amine and non-aqueous acid. So one of the ones that we just went over. So I would go with C for that one. Right. D is also the sodium methoxide, which we talked about for part B. All right. So for 16, it says to select the sequence of reactions that are going to convert the starting material to the product in the best yield. And what's different between our starting material and our final product?
We have another ketone added, right?
Yeah.
Do I need to know the position of this? Because that would be what? No, right?
You by position,
Beta.
do you mean like meta ortho?
Oh, no. Oh, well, yeah, that also, it isn't a ring. I don't know.
So when you're doing meta para ortho, that's typically designated for the benzene ring. So you wouldn't have to worry about that if
Oh,
that's what
okay,
you're asking.
perfect.
But was that what you were asking?
Oh, no. It was, yes, but as long as we don't have to worry about it, I'm not worried about it.
Yeah, I mean, because this is not a benzene ring, in terms of those positionings relative to each other, I don't know if we would have to worry about it, but we're gonna have to
Oh,
see.
okay.
With these, honestly, because you guys are doing multiple choice, for the sake of time, I guess, when you're taking your exam, so that you can make sure you get through all the problems, I would honestly personally just use the options that are given to me and see what works.
Yes, so let's do that.
Yeah. So let's do that. And so for the first part, we see Br2 and acetic acid. We see Br2 and light. So we have to pick which one would be better, Br2 and acetic acid versus Br2 and light. So definitely with Br2 and light, Br2 and light is not a super selective reaction. And you can get bromination at several different sites. It would probably be more selective for this position, just because I don't know, maybe the
Yeah.
intermediates, that free radical intermediate might be stabilized, but because of that double bond nearby and resonance. But you're gonna get bromination throughout this ring. In addition to the fact she didn't put the word excess there. And so you're going to get polybromination everywhere. I don't know, maybe I'm being too picky about it, but I feel with Dr. Bean, she'd probably put the word excess if she's going to use Br2 and light. So that's just a little clue there. But Br2 and acetic acid, let's see what that's going to do. Is that's a very selective reaction when you have these carbonyls and you have, and you want to put the bromine specifically in replacement of an alpha hydrogen. So if we put Br2 in acetic acid, we would get Br right there. Okay, so we can go with that for now and continue on and see what we get. Now, I see the next step, what I see is this sodium ethoxide, and that looks useful. Let's see what else there is. Sodium ethoxide. And then we would have a ketone after that. And then we would have H3O plus. And then the other option is pyridine. And
Ether.
pyridine and a. So okay, so if these wouldn't be ethers right here. And how can we figure out that it wouldn't be an ether?
Because it has the O in parentheses.
Exactly. Yeah. So that would be a carbonyl. Now what is confusing me a little bit. Oh, okay. Okay. It's at the end. It's an ester at the end of that. So I would honestly, I would probably say we should write these out. Between pyridine and sodium ethoxide.
Those
They're
both
both.
bases.
So they're both bases. Now,
One's
sodium
stronger.
ethoxide, I would say I would say it's probably stronger just because it has a charge on there versus pyridine doesn't. Pyridine, it's an aromatic ring.
Nitrogen, right?
Yeah, it's like
Already
pyridine.
not. Just kidding.
Pyridine, it's gonna look like that. And then you have this lone pair in an sp2 hybridized orbital, and that can go, because it's in an sp2 hybridized orbital, it's more accessible to the environment. Watch out for that as a fact question if she's asking about basicity. I've seen it in the past. So pyridine is a good base because of that, but we also have the sodium ethoxide minus charge. Okay, and so it has a minus charge, so I'd say because it has a charge, it's stronger. And then we're going to compare between the other two things that come after it, because I don't know necessarily which one would be better just based upon that fact. I mean, I was thinking that this may oh,
Mg and AC.
ooh, I see. Okay. Yeah, I think I see. Yeah, okay. So what they're trying, what I think she's trying to go for with this one, and she hasn't posted her key yet. So of course we're gonna check it alongside all of these with her key. But with this, I think what she's going for is an SN, or not an SN2. Yeah, I think she's going for. What is she going for with this? I'm not sure.
Bromine. But if bromine isn't selected, I mean, I guess we can put it anywhere then. I don't know.
I'm not sure. I'm thinking let's skip this one and come back.
Okay.
All right, just so I don't spend too much time, too much of you guys' time, I guess. So consider the reaction and mechanism that produces the product shown. Which of the following statements is true? All right, so for this one, we have sodium ethoxide and its solvent as well as heat. And so in terms of doing the mechanism, I personally would not waste my time to do the entire mechanism when the answers here are written in word format, right? So I'm not going to have to probably come up with a particular intermediate. Now let's read what these are. I mean, we know that this sodium ethoxide is a strong base, right? So right away with the mechanism, I want you guys to look to what conditions she's giving you, okay? So if she's giving you basic conditions, what charge should we not have in one of these intermediates or at some point in this reaction?
Is it a positive charge?
Yeah, we do not. You do not. No. It's a big no to have any positive charge in a mechanism under basic conditions. Okay, only negative charge or neutral, and under acidic conditions, it's a big no to have minus charges. Okay, so the first thing with these mechanisms, because honestly with multiple choice it's very unlikely she's gonna actually need you to go through the entire mechanism. We'll see for this question, but right away we want to make sure that there's not going to be any intermediate with a positive charge if we're under basic conditions. Okay, and then this is a strong base, so it's going to deprotonate. This is a symmetrical molecule, but it's going to deprotonate that alpha hydrogen, okay? So, so remember, that's what it does in terms of the mechanism. And when it does that, it's going to form this enolate. Okay, if we go straight to the most stable resonance contributor. You deprotonate that proton, you put the electrons down onto that sigma bond, and then you push the pi bond onto the oxygen, okay? And you form what's called an enolate. And an enolate, it looks like this, all right? And enolates are very reactive, similar to what we did in the Stork synthesis. Very, very similar. It can come back down, neighboring atom participation, and that can go, the pi bond can be propagated to go and attack something, for example, okay? Now, what we have here is, let's just read the options. So, I mean, we see that there's a difference here. We see the removal of a carbonyl at some point. We also see that we have this new double bond that's been created specifically at the alpha to the beta position, okay? So we have this, I believe they call it alpha beta enone or something of that sort, but it's just a alkene, a double bond that's located at the alpha carbon to the beta. So then it says the more stable carbocation produces the more substituted enone.
We won't get a carbocation, will we?
We will not. Very good catch. So there's not going to be a positive charge here. The mechanism at play does not involve any positives. I mean, firstly, because of the fact that it's under basic conditions, but also you're going to have deprotonation and you're going to form this, what is that called? The enolate, okay? And then the reaction involves the elimination of a hydroxide anion. Okay, I'm starting to like that option choice. A nucleophile formed is an enol.
Yeah, right.
Okay.
But isn't that unstable? So, oh wait, but you did say it would attack something. It would go back. Oh no, but the O would actually kick back, and it would be the alkene that would be changing, right?
So let's think, remember, we're under basic conditions. So let's think about the difference between an enol and an enolate.
It has a charge.
What's the difference here?
That one has a charge. The enolate has a negative charge.
Exactly. Whenever you add.
Oh, okay. Just kidding. So no.
So for that reason, I would personally knock that one out, just because in this mechanism, I'm thinking that we're going to have an enolate, because when we have that we're not going to protonate the oxygen at any point. And so then it says an alkoxide anion is protonated with H3O plus. Do we have any H3O plus?
Oh, okay, I was just about to say, do we just assume that H3O plus is present? But no.
Yeah, definitely not.
Basic conditions.
Definitely not, because they give you the conditions and they say, I mean, we know from the conditions that it's basic. And so if they wanted it to have a then H3O plus step, that's a different story. But it's not, there's no H3O plus to be found here. You only have ethoxide and ethanol. Okay. And so we want to cross that one out. And so what answer should we go with?
B.
Yeah, for sure. Okay. And that's how we would form this this double bond over here. So we have an elimination. That's how the double bond should form, is through an elimination, where you're gonna have yeah. Okay. So now it says, consider the reaction mechanism that produces the product shown. Which of the following statements is true? All right, so when we're comparing between these two, we see hydroxy groups, we see an aldehyde, we see sulfuric acid. So what are our conditions?
Acidic.
All right, so using that information, we're going to try to knock some things out. And then we also have the formation of what type of functional groups?
Are these ethers?
These are ethers. Yeah, very good job. And we have this ring formation. This one, honestly, it looks oddly familiar. I don't know if it was like my year of the exam, but it's giving me like flashbacks right now.
Hopefully not too bad.
Yeah.
Suppressed memories.
Yeah, I know. It's pulling up memories, really bad memories. So it looks very, very familiar for some reason. And okay, so what we have going on here, we have an aldehyde, we have these two hydroxy groups, we're under acidic conditions. And so let's look at if any of these options we can knock out just based upon the fact that we have acidic conditions.
Is it C? Would C be one?
An alkoxide anion, keyword anion, attacks the activated carbonyl carbon atom. Very good job. Right away, we can knock that out because there's never going to be a point where we're going to form an alkoxide anion. It's definitely going to be the attack of these hydroxy groups, okay? And not an alkoxide anion. But the rest part is right, that something's going to attack an activated carbonyl carbon atom, but not an alkoxide. Good job. So then protonation of the alcohol group enhances its nucleophility. Okay, so we wouldn't knock that out because of that fact. Okay, so with this, I want us to just read the option choices first before we get too carried away. So the first one says a unstable hemiacetal is formed. So what is a hemiacetal? That's something that's important, I'd say.
Yes, I definitely agree.
Not sure. So if we know, if you can remember that an acetal is this, that's an acetal. Where, and you'll see this
hemi
in
meaning
like
one,
sugars.
right?
Huh?
Sorry, now go ahead.
Okay, so you can see this in sugars and glycosidic bonds. If you're taking biochem, that's an acetal, and they're not very reactive, right? In orgo, they only teach that H3O plus is going to affect that, right? Like, remember when we had those protecting groups?
Yes.
That's an example of an acetal, and we use that so that because it's not very reactive at all. But a hemiacetal is like, because of the prefix hemi, you can think of it as it's like halfway between, almost, it's halfway to an acetal in a sense. So this on top is going to be the hemiacetal. Okay, where you're halfway there, but you still have that hydroxy group, okay? And so it's saying that we have an unstable hemiacetal, and they are unstable. The reason for that is because, let's say we're under acidic conditions here. So let's say we were to protonate this, right?
Mm-hmm.
So 1, 2, 3 bonds, and a lone pair on oxygen gives it a positive charge. And then what can this neighbor do?
It can snatch proton. Oh, just kidding.
I mean, it could do an intramolecular.
I was gonna say it'll do a proton transfer and then make a good leaving group, but just kidding.
you could totally do that, but that's not what I was going for. But that can totally happen. But it would do neighboring atom participation and push that leaving group off.
It would be a good leaving. Oh, regardless, I guess there's a good leaving group, I guess.
Yeah, so you form this good leaving group, and this neighboring atom can come in and propagate that leaving group to leave. And so that's the hemiacetal, and that answer looks really good. But let's look to the other ones. Protonation of the carbonyl oxygen's atom to make the carbonyl carbon atom less electrophilic.
Wouldn't we have more of positive charges on here, though?
So if you were to protonate this aldehyde, right, would you be making it less electrophilic, this site?
No, because you could bring back that negative charge up to the bring that bond back up to the oxygen, and then that would be a full positive charge on the.
Yeah, that resonance structure, for sure. I mean, this is activated. It's even more partially positive than it was before, because now you have a neighboring atom that's electronegative, doesn't want to have a positive charge. Now it has a positive charge. So it's actually making the protonation, which I would deem to be the first step. I would say it's the first step here. It's going to be protonation of that aldehyde. That actually makes it more electrophilic and more susceptible to attack by one of those OH groups. So for that reason, I would knock that one out. And then we can look to protonation of the alcohol group enhances its nucleophilicity.
No, that one.
Yeah, that one, it doesn't make much sense to me. On the contrary,
It would make it less of a nucleophile now. Now it's a good leaving group if you protonate the alcohol.
Yeah, it becomes a good leaving group, and I mean, you're giving it a positive charge now, and so a nucleophile likes to have excess electron density. So if you want to make an alcohol group more nucleophilic, in fact, you would deprotonate it to give it the O minus charge and give it an O minus charge. So I would cross that out, and I would go with the unstable hemiacetal is going to be formed at some point within this process. All right. Do you have any questions about that?
I don't.
Yeah, so with the first attack of that hydroxy, you're going to have a formation of one of those rings, and then keep it going. So then for number 19, we have an unknown compound that has the formula C5H8O4. And the IR spectrum exhibits a broad peak, and so on and so on. So I would before I even read the rest, let's just find what our unsaturation number is, okay?
Mm-hmm.
So everybody, wow, there's 4 oxygens. My gosh. I think that's like a record. I don't think I've ever seen 4 oxygens. I think it's typically only gone up to 3.
Right.
Okay.
She wants us to work for these now.
She's like,
so 5 times 2, right?
2 times the number of carbons, so that's 5.
Minus hydrogen.
Plus 2. Minus the number of hydrogens, which is 8, right? Does oxygen make a difference?
Divided by 2? No. Only nitrogen does, but we didn't get to that chapter, right?
Yeah. So, perfect. So we're going to get 10 to 12. 12 minus 8 is 4. 4 over 2. Did everyone get 2?
Yes. I said yes, but I don't know about everybody else.
All right. So I'm going to assume that they got 2 too. Wait 1 second. Oh, someone asked, can you post this recording? Yeah, of course. That's the whole goal, because originally I was just gonna record it myself, but then I just got so bored. To be honest with you.
And it's so early, it's just no.
Yeah, I know.
I'd be bored and tired.
My parents probably think I'm like crazy. So, so basically we got an unsaturation of 2.
Double bonds, right? Oh, well, there's gonna have to be because of all the oxygens, sort of.
Yeah, so we have some double bonds. That's going to indicate that we're not going to have a benzene ring,
Mm-hmm.
right? Because that would have to be greater than 4. So we have some double bonds of some sort, and there are going to be 2 of them. All right, we don't know which kinds. All right, and I personally would write out all these structures on my scratch paper.
Mm-hmm.
The blank page. Alrighty, so So for our first one, we have a attached to, we have a carbon attached to a CH2, 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 and then what's that functional group at the end? An aldehyde. And then we also have, for some reason, it's written like O and then H like that. Oh, okay, it's just another aldehyde. Yeah, so the first one has two aldehydes, and so this is really funny here because you can really rule out some stuff because we know that there's four oxygens.
Oh yeah, that's not
There's
gonna work.
supposed to be four oxygens. We fulfilled the unsaturation of two, but we did not have four oxygens. So right away, our molecular formula does not match. So we're gonna have to cross that one out. And then let's go to B and see what we have. So we have a what functional group at the very beginning there?
A carboxylic acid.
Yeah, we started off with a carboxylic acid, and there's going to be a specific region in the proton NMR that's going to confirm a carboxylic acid. Do
Do you know where
you
the alcohols are? Just kidding. No.
in the proton NMR?
Oh, proton NMR. I don't remember.
In the proton NMR,
Are we really far back?
yeah, it's going to be the furthest signal that we would see to the left, and it's going to be at the 12 region, 12 ppm pretty much.
Yeah.
Somewhere there. And so if we even look at our question, it does say the proton NMR displays a broad singlet at 12.1 ppm. So right away when you see that, that's carboxylic acid. And we have four oxygens to account for, so that's a high chance. So let's continue on with drawing that molecule, but keeping that in mind. So then we have a CH2, and then another CH2, and then another CH2. So this is looking like a very plausible option. And then another carboxylic acid. So here we do have the four oxygens and we do fulfill the two unsaturation. So we got to keep that one in the running. All right. And then we'll continue on with CH3.
Two alcohols connected to it?
Yeah, so they're grouped together. So when they're grouped together, with them like two alcohols, that's interesting. Two alcohols like that.
But this would have.
I don't think she would ever give this structure on like an actual
saturation
exam.
maybe two.
Well, very unlikely. I've never seen something like that before on one of her exams. So, that's C. Sorry?
For this one,
Mm-hmm.
There are no double bonds or anything on there. Would it still matter though?
Oh, true that. True that. Good catch. No unsaturation of two. Right? And so good catch. So we're gonna want to remove that. And then we have imagine if we don't have to look any further than the unsaturation and the
No.
and the fact that there's four oxygens.
Spec might be nice this time around.
Yeah. I definitely do think that spec with as multiple choice it's substantially easier. But the other sections, I think nomenclature and spec are easier as multiple choice. The others, I don't think there's as much of a difference, other than the fact that the synthesis won't be like 15 steps long and you have to recall everything by yourself.
Oh, yes.
So learn the reactions. The reactions is, I think, what's going to get the most people. Okay, so we have a CH3, and then we have what seems to be an ester, right? Because we end up with another carbon. It's a CH3.
Are the oxygens connected to each other?
So right here, this little piece right here, that's gonna be like a carbonyl carbon with an oxygen coming from the side, so an ester, and then we continue with a CH2. And then from that, we're going to continue with another ester. Yeah. Alrighty. Yeah. Okay, so we can, well, this has an unsaturation of 2. This has the 4 oxygens. I'm not going to care about counting carbons and such, even though I feel like that's probably something different too. But I really want us to examine the rest of it just because. So the IR spectrum exhibits a broad peak at 2,600 to 3,500. So what is that indicating? What type of functional groups? Broad is your keyword.
Oh, alcohols?
Yeah, OH. And so we also are going to have a strong peak at 1,700. So what would that indicate?
Carbonyls.
Yeah, carbonyls. And then the proton NMR displays a broad singlet at 12.1.
Carboxylic acids.
Yeah, we right there. I mean, just from that, honestly, we could have gotten our answer. If you know that 12.1 is carboxylic acids, and I was told that she is going to indeed give you guys that spec table, I think.
Yes, she said we could scroll all the way back up if we want to.
Yeah, so that's super helpful. So if you look at your chart and you see that 12 is a carboxylic acid, and that's the only one that has that. So we'll go with that.
Yay.
All right. I encourage you guys to check maybe the multiplet later, just for practice in case. And then for 20, we have an unknown compound that has the formula C6H12O3. And so we want to find the unsaturation for that one as well. All right, so we want to do 2 times the number of carbons plus 2 minus number of hydrogens. How many carbons we have? 6. Number of hydrogens we have is 12. Oxygens make no difference. We have 3 of them, and we're going to divide it by 2. All right, so we get 12, 14. So what did you get as your unsaturation?
1.
Yeah, I got 1 as well. So no benzene ring for this one either.
So the answer is D. No, I'm kidding.
Is that the only
no,
one?
I'm kidding. I'm kidding. Because the other one's the CO. Those are carbonyls, no?
Huh?
Nothing. Never mind. Just kidding.
Yes, those are carbonyls. You're exactly right. But you also you also have carbonyls in the other ones. But like C, for example, it has a carboxylic acid at the end, and so that's 2. That would be an unsaturation of 2.
Yeah. Oh no, I was saying D, but then I was like, just kidding. I don't know. Oh.
Imagine, I'll be like, wow, Elsa has like superpowers. But we can cross out C if you're trying to go that route as well. Oh my gosh, as well as A.
Right. I'm kidding. Okay.
Jeez. Wait, you might be right. Okay, let's just continue.
That's what I was saying. But I was like, no, let's just focus on I'm working it out, right?
Yeah. So I thought you were just joking. So let's just continue with it as though it was a normal one this time instead, just to get to go through it. So the IR spectrum exhibits strong peaks at 1742. So what is that going to most likely indicate?
1742 is carbonyl, right?
Yeah, it's going to be a carbonyl. It's a little bit higher frequency or wave number in comparison to the last one, but it's still in that carbonyl region, and it says that it's strong. So if on your table you see S beside, that means strong.
Mm-hmm.
And you'll see like medium
and 1242 like variable. Is that an ester?
And then
an ether, sorry.
Yeah. In B? An ether?
Yeah. Oh, no. I was asking about 1248. Is that significant?
Oh, Yeah, so 1248, it's interesting. 1248, that's actually located in your fingerprint region, which you typically does not even want you guys to look in there. But yeah, that's indicating an ether. So if you're like super checking in the fingerprint region and you can analyze it and it's clear and you see a specific strong peak, that would be indicative of an ether, because that's your region for the single bonds of carbon to oxygen. So yeah, an ether. So that helps us out as well. The proton NMR is going to display a 2-proton triplet at 4.3 ppm. So 2H is going to be representing what type of group?
CH2.
Yeah, CH2. I wouldn't work. I mean, the fact that it's 4.3 means that it's going to be close to the oxygen. 2H triplet at 3.75 ppm. That's going to be another CH2.
A little further away.
A little bit further away from the oxygen. Could be close maybe to a carbonyl that has an oxygen, but maybe a little bit further from the oxygen. But then, like, it could maybe be, right? And then we have a 2H quartet. That's a CH2 as well. That's going to be like it's going to be next to a CH3.
That's a quartet. Yeah.
Yeah. And then we have a 3H singlet at 2.1. So that's going to be your ordinary CH3 group that's connected to something that does not have. Yeah, to something that does not have any protons, because it's a singlet, right? And so that's confirming D right now. And then we have another CH3 that's a triplet, which is going to be this one over here. Because it's a triplet, it means it's connected to a CH2. And of course, it's at 1 point.
Oh, Sabrina, are you writing?
Oh, is it not? Yes.
It did it again, I think. I don't know if you were writing or if you weren't, but if you... Oh, there you go.
No. Yeah, I am, but I was only underlying.
Oh, okay. Okay, I was like, wait.
No, you're good.
Okay, go ahead. Sorry.
Yeah. And then, so yeah, we're going to get D from this. For sure, it confirms it. We have a CH3 with an ester in there, and so that's accounting for our carbonyl, and that's accounting for our unsaturation of 1. Then we have CH2, CH2, which are all explained by that proton NMR. We have the ether that's explained by the 1248, as well as that's our third oxygen. So if we weren't given that 1248, you would know that from the fact that there's not an alcohol, and you have another oxygen, all right, and you have the right number of carbons and such. So it's and you can't have another carbonyl because of the unsaturation. And then we end up with the CH2 CH3, which we see from our proton NMR. So for sure, I would go with D.
Okay.
Does anyone have any questions?
I have a question. Would you mind just like talking over the unsaturations, how we know? Because I've never learned that before. Like I've never had to use it.
Oh, okay. Yeah, for sure I will. Here, give me 1 second. I want to grab my charger really quick because it's about to die.
Okay, sure.
And that would be bad. We've been recording for like...
No, it's okay.
hours?
I have all the answers there.
Yeah, you guys were here.
Right.
For the other, like, I don't know how many people in Orgo. 400, 600?
Oh, I don't know. That's a good question. Too many.
Yeah. All right, it's charging. Yeah, so that's a good question about the unsaturation. So the reason why I say to look to the unsaturation at the very beginning, especially with this multiple choice, is you can rule out a lot of these options just by knowing the unsaturation. So the unsaturation is going to tell you how unsaturated your molecule is. And in other words, how many double bonds or triple bonds or rings that you have, because a fully saturated molecule is one that has the full amount of hydrogens on it. Okay, And so once it becomes unsaturated, if you remove a proton or a hydrogen and you put a double bond, you see how we're decreasing the number of hydrogens?
Yes.
When we go from this to that.
Yeah.
So it's the same, it's the same number of carbons, but now that we introduce a double bond, we're unsaturating the molecule. And so calculating that unsaturation number is going to tell us about how many double bonds we have, or if we have, for example, a benzene ring, depending on that number. So you use the specific formula that I put here, and that's going to be the number of carbons multiplied times 2. And so this is the number of carbons in 6. And then we multiply it times 2, and we add 2 to that. And the reason why we do that is we're trying to find, if we had a fully saturated molecule, how many protons should it have? How many hydrogens should it have? And then from that, we want to subtract how many protons we actually have on our particular compound of question. And so that's where we input the number of hydrogens over here. So that's going to be 12. And then in order to just get it into degree of unsaturation, you divide it by 2. And so that's your formula there.
So I've always done the formula, and I've always, because I know that's what Beam says, to always do that first. So I'm good with that part, but I just don't, because normally we've always gotten 5 or 4, I guess. So you know that there's a ring. That's what she likes to use a lot of times.
Mm-hmm.
But I'm not good with 2. So if there's 2 or if there's 1, like you guys said on the number 19 about having the carbonyls, because we had an unsaturation of 2 there. So if I have 2, I know that I'm going to have 2 double bonds. Is that what it is? Or
yes, exactly. So each double bond that you add would be an unsaturation of 1.
okay.
And so, or rather, a better way to say it would be each pi bond that you add. So like, let's say we had a triple bond like that. What would be the degree of unsaturation of 1 triple bond in the molecule?
2. Would it be, I don't,
3.
would it be 3?
It'd be 2 because you have 2 pi bonds.
2 pi bonds, yeah.
But you have 1 sigma bond, but you have 2 pi bonds. And so with each pi bond that you add, you're getting 1 extra unsaturation.
Okay.
But she may give you guys a triple bond. It's very unlikely, most likely, since this is like the carboxylic acid section chapter, that it's most often she's going to give like an ester or a carboxylic acid or even a ketone or an ether.
I forgot about that. That's true.
So the unsaturation number is super useful. I mean, even more so now that we're doing multiple choice, but it's super useful to know how many double bonds you have. Or if you, like you said, if you have a ring. So if you see an unsaturation of 4, you have, can you guys still see me drawing?
Yes.
Yeah, so you would have like 1, 2, 3. So you have 3 pi bonds, and then you have 1 ring. And so that would be an unsaturation of 4. Because a ring is also a degree of unsaturation. A ring, a double bond, like a ring or a pi bond is one, each one of those would be a ring, a degree of unsaturation.
Okay, great. Thank you so much.
Does that make sense?
Helps a lot. Yeah.
Of course.
It helps knowing the why behind what I'm doing. So that helps.
For sure. For sure. And I wanted to go back to that previous question. I'm trying to, I'm blanking out on the difference here with the sodium ethoxide and the pyridine. I'm thinking to go look this up and then address this question at a later time.
Yes.
Unless if you guys can remember something from lecture. Do you guys remember anything that she mentioned about?
What chapter do you think?
It's gonna do protonate. They're all. See if there's a way to.
Chapter.
Oh, I can pause this recording.
Condensation.
So resume. All right, guys, so we looked into question number 16, and it happens to be something that she has not actually covered yet in lecture. She will get to it this Thursday, and so I'm gonna just let you guys know that we solved for the answer, and the answer is C. If you're trying to figure it out on your own, this deals with the Michael reaction with the Michael donor as well as the Michael acceptor, and so try it out and see if you can figure that one out. All right, and just feel free to ask any questions, but she's going to cover this one on Thursday. All right, and for you guys that are here, do you have any other questions you want to ask at the end? No, y'all are good, y'all are okay.
Oh, thank you.
Yeah, you did an amazing job. That was
Thank you.
my question.
Thank you, guys. Good job answering questions and being proactive. You got this, okay? Good luck, everybody.
Thank you.
Thank you.